All right, welcome everyone to this week Autonomy Talks. This week is a pleasure to have with us Professor Oren Salzman, who is a professor in the computer science department at the Israel Institute of Technology. So something about Oren. Oren completed his PhD in the School of Computer Science at the Tel Aviv University, working under the supervision of Professor Dan Halperin. He then moved to US, where he was a postdoctoral researcher at Carnegie Mellon, working with Siddhartha Srinivasa. And he also worked with Maxim Likachev, who was a research scientist at the National Robotics Engineering Center. His research focuses on revisiting classical computer science algorithms, tools, and paradigms to address the computational challenges that arise when planning motion for robots. And you probably know him for various works on planning in different domains. He combines different techniques coming from diverse domains, such as computational geometry, graph theory, and machine learning. And he strives to provide efficient algorithms with rigorous analysis for robot systems with many degrees of freedom. Today's talk will be more focused on the application of minimally invasive robotic surgery. And we are all very interested in the talk, and therefore I give you the stage, Oren.
Thank you. Thank you for the introduction. Thank you for having me here. So before I start, I think it'd be nicer for everyone, if you have any questions throughout the talk, feel free to just interrupt and shout out the questions. I prefer to have it as a conversation and not as a lecture. And as mentioned in the introduction, my research typically focuses on the algorithmic part, algorithmic motion planning. And this talk is it's kind of a cool experience for me. It's part of an ongoing journey where we're seeing how to apply a lot of the tools and the algorithmic machinery that we've developed to the domain of minimally invasive robotic surgery. So I need to make a disclaimer here that I know very little about the clinical aspect of this talk, and it's all done through a series of amazing collaborators who know much better the domain, the challenges, and the specific details that are relevant there. So I need to apologize in advance if I make any oversimplification or inaccuracies on the medical side. So that's kind of a disclaimer. And with that disclaimer, it's probably a good start to embarrass myself by talking about the medical applications or medical procedures. And we're going to talk about two different procedures: site reaching, where we want to reach a specific site within the body, say to perform biopsy or to deliver some therapeutic device. And the second application is inspecting some site. In this example, endoscopic inspection of anatomical cavities. So these are kind of two medical procedures that we're going to focus on throughout this conversation or this talk. And before we can describe them, we first need to ask, why do we need these medical robots? And to answer that, we need to understand how traditionally these applications that I mentioned were done. So if we want to reach a target, the kind of old school or standard way was using rigid devices with very limited maneuverability. So say to perform a biopsy, this is an example of a biopsy needle. And the surgeon's decision was to choose the puncture site or some entry region. And then there was nothing to do except push the needle forward in a straight line in order to reach the target. In this example, we have these red blurbs which depict anatomical obstacles, and we see that the device gets dangerously close to one of these obstacles. And in the past years, we have these new devices. We call them steerable needles. So this is an example of a steerable needle. Can you see the video at a reasonable frequency? Yeah, okay. And as you can see from the video, they can take curved trajectories, which allows us to to avoid getting close to obstacles. So in this kind of cartoon, we see the green path taken by the steerable needle, and we see that it kind of safely steers away from the 2 red obstacles in contrast to the one with the rigid device. If we look at the inspection planning problem, an ongoing, a running example that I'm going to use is inspection of the pleural cavity. That's the region between the chest wall and the lungs. And this is kind of the most horrific medical figure that I'm going to show. So for those of you faint of heart, if you manage to pass this slide, then we're good. And this is the figure on the left. We can see traditional inspection of the pleural cavity. And on the right, we see this very weird robot. You can barely see the robot. We have 2 manipulators that move outside the human body. This is called the Continuum Reconfigurable Incisionless Surgical Parallel Robot, or CRISP robot. And from now on, I'm only going to say CRISP robot because I can't say it again. And we see that it has this needle diameter tubes that assemble into a parallel structure inside the rib cage. And we're going to have a camera mounted, a chip-tip camera mounted at the end of one of these tubes, which is going to allow us to inspect the region of interest that we care about. So I hope that you can see that with these medical devices, we have the potential to dramatically reduce patient trauma, either or both by causing less pain and shorter recovery time and reduce patient risk. We can steer away from anatomical obstacles. And really, we can enable things that were previously infeasible. So now we're talking with a pediatric surgeon in New York who wants to apply some of the methods that we're developing, because right now he can't reach into the deep tissue of lungs of children because everything there is so small and so hard to maneuver. So really, medical robots in this context have the potential to alter the landscape of current surgery. So what's the problem? On the left, we see the kinematic model of one of these steerable needles, which has 2 degrees of freedom. We can rotate the base or push it. On the right, we can see a video, I hope you can see it, where the manipulators are moving and the tip of the robot is following a circle in 3D. And I hope I don't need to convince you that really manipulating both these devices and the other devices that I'm going to describe today is not really feasible by a human operator, no matter how experienced he is. So really, to effectively deploy these robots, we have to have autonomous motion planning capabilities. And this is not new. So those of you who've been in any robotics community, robotics conference, say in the past 10, 15 years, you probably stumbled upon one of these sessions. And back in 2008, there's been already a book on motion planning in medicine. But really, these methods didn't have any guarantees on the quality of the solution, on if a solution can be returned. And what we're trying to argue in this line of work is that in order for these type of procedures to be clinically accepted, it's really critical, both from a patient care, a safety, and a regulatory perspective, to certify the correctness and effectiveness of our planning algorithms. And this is kind of the journey that we've been taking throughout the past several years. And it's great to be in this seminar because a lot of the work or the guarantees that we can offer are building on the seminal work that Emilio did with Sertac Karman back in 2011 on RT star, and really laying out the algorithmic building blocks and proofs that allow us to certify the correctness and effectiveness of these algorithms. So that's kind of cool. And what I'm going to do in however time I have is kind of go over different applications of sight reaching. And for each application, I'm going to look at a different type of robots. I think I'm talking about 3 different robots just to showcase the variety of these different robots. For each one, I'm going to present the problem, the robot, and the motion planning algorithm that is associated with it. And feel free to stop me at any point, and we can also kind of jump on certain parts, and we'll play it by ear. So the first robot that I want to discuss is what's called a concentric-tube robot, or a CTR. And these are tentacle-like devices. So we see here a CTR of 3 tubes. And you can see there, each one is pre-curved and they're nested one within the other. The way we can control it is either rotate each tube at the base, or we can translate it. So each tube has 2 degrees of freedom. In this CTR on the right, we have 3 tubes, so that's 6 degrees of freedom. And you can see the size. And this is a video depicting the motion. And I hope you can see it's kind of like a elephant trunk-like motion, which is really cool, but also really unintuitive. If you need to try to do this manually while avoiding obstacles, it's infeasible for any user. So the first kind of planning problem that we're going to look at is how can we follow a path with the tip of the robot that the surgeon gave us as closely as possible. So in this example, we want to come in through the nasal cavity in order to either reach the brain or the back of the eye. As the dean in my school likes to say it, Oren's research focuses on picking your nose with a robot. So that's how they look at my work. And here we see on the line above, we see this CTR in simulation. On the row on the bottom, we can see it's a real CTR, not operating inside a patient, but inside a 3D printed model of a skull. And we see the yellow path that is marked by the surgeon. Say we want to cut a window through the skull in order to reach the brain, and the surgeon marked the window that we want to use laser to cut it. And we want to follow that path as closely as possible. Now, I think I should have mentioned this earlier, but nothing that I'm going to talk about is FDA approved. So all of this is, in my mind, almost science fiction. And what we're trying to do in this line of work is really turn this fantasy into reality in order to really alter the landscape of medical surgery. So let's try to formalize this problem. We're given a reference path in task space. So this is in the space of the robot's end effector. And our planning problem calls for computing a collision-free path whose forward kinematics, so for each one of these collision-free paths, we want to look at the tip of that path, at the tip of the robot while executing that path. And we want it to be as close as possible to the reference path. And if you're still a bit confused, that's fine, because this is still ill-defined. We need to define how do we measure distances between paths. These are not points, but complete paths. And we need to give some metric here. And then we need to answer the optimization problem or the planning problem on how do we plan. So the first thing we're going to do is borrow tools from computational geometry. Who here knows about Forshape distance? Just by a raise of hand. I assume that everyone's either sleeping or it's a no. So the Forshape distance is a similarity measure that accounts for both kind of the location and the ordering of points along the path. Right, there's hard chat. Okay, thank you for the response. So a typical explanation of how the Forshape distance is defined, and I don't have the time to explain why it's the best metric that we found here, is using the analogy of a man walking his dog. And the man is walking on his path, It's going to be the blue path in this example, and the dog is walking on his path. It's going to be the red path. In contrast to my dog, who never listens to me, this dog is well behaved. And they want to coordinate their motions so the person can take the shortest leash possible so they're still connected. So when they leave the house, there's some minimal length of the leash, and then they can coordinate their motion. So here the leash is actually shorter, and here the leash gets longer. And at some point, there's this maximal leash length that they have to use in order to stay connected. And finding the maximal leash length defines the Forshape distance. And it's very suitable for our task because it both accounts for where we are in the path and how do we simultaneously progress along this path. So we answered the question of distances between paths. The question is, how do we measure?
Oren?
Yes.
Oren?
Yes.
Sorry for interrupting. So, but then that implies that there is some form of a time parameterization.
Yes, yes.
Or not.
So actually
And
the optimization.
Why do you care? Why do you care about the time parameterization? I guess that if you need to insert a needle somewhere, time doesn't really. Okay, so you want to do it in a reasonable time, right? But the time parameterization, I don't see how it enters the picture.
Yes, yes. So that's a good question, and we're going to talk about, or hopefully, we're going to talk about what metric do we care about when we insert needles. So notice that here we're not inserting needles, but a CTR. The time parameterization is just used to define distances. So if we go back to this example, and we have the path that the surgeon gave us and the path that we're creating, and we want to ask how close are they? In some sense, what we want is for points on the red path to be close to points on the blue path. That's called the one-way Hausdorff distance. And we also want points on the blue path to be close to the red path. That's called the two-way Hausdorff distance. But still, you can have nasty cases where you go forward on the blue path while going backwards on the red path. And this can be a big no-no when you're performing surgery, because you want to really follow the ordering of points along the path that the surgeon gave you. And the time parameterization is not something that we care about explicitly, but it's a way, a proxy to define distances between paths. We're never going to follow the path. We're never going to implement this time parameterization. I hope that answers the question.
Okay, so in a sense, is a proxy to say that you do not allow backtracking, in a sense.
It's a proxy to saying,
so
I want the blue to be close to the red to be close to the blue, and that there's a monotonicity in progressing.
And there is a monotonicity. Okay. So that I get. Okay, fine. Thank you.
No problem. But you'll see that this kind of comes back to bite us because we lose Bellman's principle of optimality in a second. So it's not all that good. So let's give a few algorithms. We're going to build the algorithm progressively. So we have this reference path, and it's in task space. And the first thing that we're going to do is simply sample points on this reference path. So we have a bunch of points. Now we want to compute a path in the configuration space. So for each path, we need to compute the inverse kinematics. But we're not going to do one. We're going to compute several IK solutions for each sample. And then kind of the natural thing to do is create a layered graph. So in a layered graph, every point corresponding to the same task space point is going to be connected. So we have these layers corresponding to points on the reference path. And then we're going to connect every point in each layer to the point in the following layer. And then we can find a minimal cost path in this layered graph. So we can redefine our optimization problem as we're going to look at all paths in our layered graph. For each one, we're going to compute its forward kinematics. Then we can compute the discrete Forshape distance with the reference path and choose the one that minimizes this distance. And if we do things naively, it's a mess, because if we have n layers and k paths, we can't run Dijkstra's algorithm on this path because our distance metric is defined over paths. So things become a bit messy, and naively enumerating all paths is exponential in the number of layers and IK solutions. And here you need to jump through some hoops, adapt existing machinery from computational geometry, and then we can do it in time that is polynomial in the number of layers and IK solutions. So I hope you believe me here, but this is kind of a non-trivial optimization step. And since we care about theory, we started this work and we said, okay, let's see what can we say about this path. And as long as our configuration space contains a well-behaved portion, which I'm not going to define formally, and you'll see why in a second, then the algorithm is asymptotically optimal, as long as we incrementally densify the number of samples, both the number of IK solutions and the number of layers, which is really cool. And we were happy and we published this work. And then we came to apply it on the medical domain, and we got garbage. Sorry, before the garbage. It did outperform everything, the optimization-based algorithm that solved this problem beforehand. And this is an example on Herb, which is one of Sid's robot. But really for the medical domain, which is what we care about, things did not work. And the reason is, and that's kind of why theory is important, but it's also important to evaluate how realistic your theory is. Our notion of well-behavedness simply did not apply to the medical setting. So no one told people that they're supposed to be well-behaved. I definitely know that my kids aren't, and it doesn't matter how good the theory is if in practice nothing works. And I can try to give you an intuition why things don't work here. Recall that the surgeon who gave us the reference path, he doesn't know anything about the kinematic constraints of the robot, the reachability constraints of the robot. He says, I need the end effector to follow this tip. And there's kind of two things that can cause obstacles in the IK mapping of the reference path. First of all, points can be simply beyond the reachability of our reference path. So this is pi double prime here. Or points can be just simply unreachable because there's obstacles in our configuration space that don't allow the robot to reach specific points on the reference path. So there may be entire sections, entire points on the reference path that no IK solution can give us a collision-free configuration. What this means in our algorithm is that we may have a reference layer that is completely blocked. So no matter how much we incrementally densify it, we're just going to add more and more points and more layers, but we're forcing our algorithm to pass through each one of these layers, and it's never going to be able to bypass a layer that's completely in collision. And we realized this only when we came to apply this algorithm to this domain. And then Schertl, which is one of Sid's students who worked with us on this problem, he suggested a very simple modification inspired by kind of the common wisdom that we have in sampling-based algorithms, where what we want to do is connect every point not to its subsequent layer, which has an application meaning, but to a set of nearest neighbors. Because we have this common wisdom that we want to do these small motions in the C space. And this allows us to bypass points in that are not necessarily in subsequent layers. And this very small modification allowed us to solve results for a medical domain. So here we have a bunch of reference paths, some that we just defined for the sake of our experiments. And the original version just failed miserably. And we compared it to some greedy algorithm and constrained bidirectional RT. And we can see that the Forshape distance, which is on the y-axis, is much smaller for the nearest neighbor graph that I just described as a function of time, which is great. And we ran it, and I hope you can see the tip of the robot following the reference path that I kind of visualized earlier. Was hard to depict it on this 3D printed skull. And in reality, we had much bigger errors. These were primarily due to inaccuracies in the kinematic model. So it's very hard to model these crazy robots. Since I'm a bit slower on time, I'm going to skip this part, but I want to say that robot placement matters. And I'm going to run through this. And where we place the base of the robot makes a huge difference. Here we see that for some placement, we couldn't reach the corner. And by optimizing over the placement, we could reach it. So the optimization problem is actually we need to optimize over all placements of the robot. And again, we had to do use some common tools in the literature, but using the planner in our previous iteration semi-intelligently in order to speed up this process. And then we could compute the optimal placement of the robots. So I know I didn't give you any details, but I just want to give you a flavor that it's a nested sequence of optimization problems that we care about for this domain because it's so constrained. With that, I want to move to steerable needles, and we're going to talk in a minute about optimization metrics. So I defined these needles. We have here 2 degrees of freedom. We can rotate the base and we can push it forward. And these, in contrast to the CTR, which operated in the free space, these devices need friction in order to curve around the anatomical obstacles. So here we see the robot in gel. And surprisingly, one of the questions that we asked is, what do we care about? So obviously, we can bend around anatomical obstacles, and this may be safer. However, these curved trajectories increase the risk of so-called shearing. So the forces applied by the needle shaft can actually shear the tissue. What we see here is not blood, don't worry, but the needle just sheared the tissue, and then researchers at Bob Webster's group from Vanderbilt inserted red dye that colored all the part of the tissue that was torn. And we can see this huge red part colored by the dye. So the question is, do we really want to care about the shortest path, or do we want to optimize for some other metric? And what people usually did was either optimize for length or clearance, but these don't account for the forces applied by the needle shaft on the tissue. And then together with researchers at the University of Utah, this was with Alan Kuntz and his group, they defined a kinematic model that allows to model these forces. And I cannot explain anything about this model. It uses Coursera spring models. And surprisingly or unsurprisingly, this depends on the entire needle trajectory. So just like in the previous setting, again, Bellman's principle of optimality won't hold because we need to look at the entire trajectory for our optimization problem. And now I'm going to force you to participate. We have here 2 paths going from a start to the goal. Both, believe me, have exactly the same length and exactly the same curvature. And I want to ask you which one is better. And I need at least 3 answers. Someone said the bottom. Andrea, thank you. Okay, so we have an agreement on the bottom. And the answer is, your intuition is correct. So if we first take the small motion and then bend, there's going to be a lot of moment applied to this part. And the top part of the needle is going to try to apply a lot of force against the tissues. So in some sense, we can have two paths that have exactly the same length, the same clearance, but one is significantly better than the other. And for me, that was surprising. And once you see it, very intuitive, which was super cool. And once we have a model of forces applied, what we want to do is minimize the maximal tissue force applied along the trajectory. And this is called the bottleneck cost of a path. Now, how do we optimize using the bottleneck cost of a path? And typical existing planners that have guarantees on the quality of the solution require solving two-point boundary value problems or can't easily be adapted to use a bottleneck cost. And here we kind of applied a very, very simple trick. It's so simple that I need one slide to show the algorithm, and I can explain the entire algorithm and you can prove it very trivially. And the idea is to, in order to solve the bottleneck costs problem, we can apply any probabilistically complete planner. And instead of giving an optimal solution, we're going to give an asymptotically near optimal solution. So for any given approximation factor epsilon, our algorithm asymptotically is going to converge to a path that is at most 1 times epsilon the cost of the optimal solution. And the way we do it is very straightforward. We run our probabilistically complete planner, given the approximation factor, and we start with no bound on the quality of the solution. So the first solution returned by our planner is simply going to be a path, if one exists, and it's going to have some clearance. That's going to be the maximal forces applied on the tissue in our setting. Then we're going to divide the upper bound on the cost by 1 plus epsilon and rerun the algorithm. If a solution, and then we're going to rerun the algorithm while considering every point that applies more than this amount of force as an in-collision point. If no solution exists, then we know that we're not too far away from the optimum. If a solution exists, then since our algorithm is probabilistically complete, it's going to find this. And that's the algorithm. And this ensures us, I hope you can see it or kind of have an intuition, that we're going to converge to a solution that is not too far away from the optimum, which is great. What I really liked in this context is that we compared two planners, one optimizing force. This is what I just described. And second is kind of a traditional planner optimizing length. On the figure to the left, we see path length as a function of time, and we see that there's no statistical difference between the two. So the force optimizer is a bit lower, but with the error margins, they're practically the same. On the other hand, on the right, we see that the force optimizer really produces paths that damage less the tissue. And in some sense, it makes sense. We don't want to have paths that are too long because that will cause a lot of forces applied to the tissue. But optimizing for force allows us to choose among all short paths, the paths that really minimize forces applied on the tissue, just like in the pop quiz that I gave you, and that you kind of identified that within the two paths of the same length, there's one that is significantly better. So we know what we want to optimize. Let's talk about some algorithms that solve a optimization problem. So let's even go back to finding a shortest path. Even that's a hard problem. And the question we wanted to ask is what can we say about these planners? So going back to the theory, we have different guarantees that the planner can offer. A planner can be complete, which means if a solution exists, it'll find it in finite time, and if not, it will report failure. What we're used to in our community is probabilistic completeness, is that if a solution exists, then asymptotically, it will be able to find it. If not, then we're kind of stuck and we have no guarantees. There's a third notion that has been floating around, and I've been surprised at how much there's no clear definition of resolution completeness. So a resolution complete algorithm is one that in finite time will report if a solution exists within a predefined resolution or report failure otherwise. And this is kind of hand wavy, and the devils are in the details. And what does it mean within a predefined resolution? And what does it even mean a resolution, especially looking at the differences between holonomic and non-holonomic algorithms, systems, and really proving that a planner is resolution complete, even given the existing machinery that has been floating out there, took us about 5 or 6 pages of an appendix to really nail down the different details. So this should be corrected. It's still work in progress, but I'll talk about updates. So as far as we were aware of, there was no previously developed planner for these types of systems that offer any formal guarantee on the quality of the solution, if a solution exists, or that is able to report that no solution exists. And what we do in this line of work is introduce the first planner for these types of systems that, under clinically appropriate assumptions, which is really cool, can guarantee in finite time if a solution exists, and if so, report it. Not only that, in contrast to the previous example where we had a bunch of theory, but it was irrelevant, this is done while outperforming state-of-the-art planners. And I'm going to give you some intuition on how this is done. So here we have this approach that is a combination of several algorithmic building blocks. On the one hand, we have a set of carefully designed motion primitives. For those of you who aren't familiar with motion primitives, these are a set of pre-computed motions that the system can take. And we apply them within a multi-resolution framework. So we have a bunch of primitives, each one within different resolutions, and then we can combine them into a planning architecture. So the ability to take large motions when we're progressing towards the goal, and taking fine motions when needed, and the search algorithm kind of understanding when to do what, is the notion of multi-resolution planning. So here we have to refine these motion primitives. And we needed to apply a lot of domain-specific optimizations like parallelization and culling and exploiting the fact that these systems have curvature constraints, so they can't go anywhere. And this allows us to reject configurations that we can't reach them. And the combination of these 3 building blocks allowed us to suggest an efficient and resolution complete needle planner. So this was presented last year at RSS, and results from ICRA came yesterday for us. I don't know time-wise when it came for you. So the resolution complete planner was presented last year at ICRA, and then we moved from resolution completeness to resolution optimality. So we're within the technical explanation of what resolution optimal. I don't have time to dive into it here, but we can also give guarantees on the quality of the solution. And here we can see the planner in action applied for accessing a nodule within the lung. With that, I want to move, and I think I'm good on time, to our third application and our third robot, which is site inspecting. So here we have this CRISP robot that I mentioned earlier, And we want to use a camera at the tip of this robot to inspect some region of interest. So here is kind of a better visualization of the robot. It has several tubes. One tube is a camera tube, and we can see, and it's very hard to see, but at the end is a very small camera. Here we can see the same system in simulation, and we can see in green where the camera, the point of view of the field of view of the camera. And here we can see a visualization and simulation of the system in action. This was presented at RSS, I think 2019. And you can see this very unintuitive motion taken by the robot. The points of interest are discretized using a point cloud. And you can see that at specific points, it takes a snapshot in order to view these points of interest. So let's try to formalize this problem, since this is one of the non-standard planning problems. We have a workspace and associated configuration space. And we have, what's different here, we have K points of interest that we want to inspect. And the way we inspect it, we're going to abstract everything about the sensor simply as a mapping between the configuration space to subsets of points of interest that can be seen from a specific configuration. So I'm not going to go into exactly which sensor we're using, just assuming we have this mapping between configurations and which points of interest we can see from these configurations. And the inspection planning problem calls for a collision-free path of the robot, starting at some initial configuration, such that the points viewed along this path, the points of interest viewed along this path are maximized. And among all of these paths, we want to choose the one that has the minimal length. And this is a hard planning problem. So we know that motion planning is already p-space hard. And here we need to account for also the coverage, what we see while moving along a path. And the same thing that we saw in the previous two example of Bellman's principle of optimality doesn't hold. So again, there may be a setting where right now we see a very small subset of the points of interest, but it's worthwhile to take this route. And later we're going to see much more points of interest. And I'm going to give a very small toy example in a second. So the approach, very similar to the sampling-based paradigm, is cast a continuous inspection planning problem to a discrete version on a graph. This graph is going to be a bit different than, I don't know, PRM ruler maps. And then we're going to have a very hard problem of how to search this discrete graph. And since we want to converge to the asymptotically optimal path, we're going to incrementally update the discrete structure and recompute paths in this graph. So this is kind of an approach. We're going to use RT and RG to, I assume that everybody here knows about RGs. If you don't, they are, roughly speaking, this is a graph such that RT star is a subtree of this graph. And we know that paths in this graph converge asymptotically to optimal paths to the goal. That's kind of a very hand-wavy description of RG. And the idea is to use the RT and RG to search the configuration space without accounting for coverage. And the reason we're going to use RGs is because it's a graph. And as we're going to see in a second, we may want to retrace our steps. And up until this third block, we're ignoring coverage. And then using this graph, we're going to construct a so-called inspection graph. I'm going to define this, which will allow us to solve the inspection planning problem. Having said that, this graph is going to be just an awful construction. It's going to be huge, and there's no way that any search algorithm is going to be able to solve it. So we're going to have to, again, resort from optimality to near optimality. And near optimality is kind of defined trickily here. And in order to converge to the optimal path, we're going to decrease our approximation factor as we add more nodes to our tree, and that's going to allow us convergence to the optimal path. So let's kind of break down this algorithmic approach to different steps. And the one I want to concentrate is the inspection graph. I assume that you guys are familiar with RTs and RGs. And before I want to do that, I want to explain why we need a graph and how inspection paths look like. So let's look at this kind of toy example. We have here vertices, in this case, A, B, C, and D. From each vertex, we have a set of associated points of interest that we can see. So from point A, we don't see anything. From point B, we see point of interest 0. And from point C and D, we see point of interest 1. And we want to compute a path that sees all points of interest, so 0 and 1. How does the optimal path look here? We start at A, we go to D, we retrace our path to A. So notice that our path visited A twice, but at the first time we were at A, the coverage seen along this path is the empty set, while the second time we already saw point of interest 1. So the coverage chain, and then we can go to B. And that's why we can have loops in this graph. So the question is, how do we use search machinery to account for this challenge? And the way we solved it is using a so-called inspection graph. What we do is for each subset of points of interest, we're going to create a layer corresponding to all points of the original graph. So what we do, nodes in this new graph are going to be pairs. And I'm going to, again, explain this on this example of a vertex in the original graph and a subset of points of interest. And an edge connects two vertices. If there's an edge connecting the first component in the original graph, and the addition and the point of interest that I saw leading to the source of this edge added to the point of interest that I see at the target equal the point of interest, the set of points of interest that I see at this new vertex. So that's kind of very complicated, but the idea is simple. If we look at the path that we saw going from A to D, back to A and to B. So we have all vertices in the original graph. Each one is associated with the subsets of points of interest. So the empty set, 0, 1, and 0, 1. And the path that we saw earlier goes from A to D. So we start at A, seeing nothing. We go to D, and now we already see point of interest 1. We go back to A, and notice that this is a different version of the vertex A because we see a different subset of point of interest. And then we move to B, and we see the entire sets of points of interest. Oops. Again, a question to you guys. How do we solve the inspection planning problem given this inspection graph? The answer is on the slide, but you need to not lose me completely to be able to see it. So solving the inspection planning problem corresponds to computing the shortest path to any vertex in the top layer. So if we got from our source to any vertex in the top layer, it means that we saw in any vertex in the top layer sees all points of interest. And we just want to compute the shortest path. So we reduce the problem of inspection planning where we have loops in our graph just to a shortest path problem. The problem is that the graph here, its size is exponential in the number of points of interest because we have this copy of the original graph for each one of the subsets of points of interest. And the way to do it is to relax optimality to near optimality. And here a path is said to be near optimal for two approximation factors. Here we need to both relax path length and path coverage. If what we see is not too much far away from what the optimal path saw, namely we see p% of what the optimal path saw, and path length is not too far away from the length of the optimal path. Namely, we're not more than 1 plus epsilon away from the length of the optimal path. And I want to leave time to questions. So using the notion of near optimality allows us to dramatically prune away parts of the search space, and to suggest an algorithm that computes a path that epsilon p dominates the optimal path. So we're not too far away from it. And using a bunch of algorithmic tricks of lazy computation and applying heuristics and incremental densification and lifelong planning and how to sample, we can get an efficient algorithm. So if we look at coverage as a function of time, we can see that the state-of-the-art roughly produce 40% coverage, even after we gave it several hours to run. And different versions of our algorithms, this is with different instantiations, obtained almost 80% coverage. And the actual results is slightly higher because some points of interest cannot be viewed. We also need to look at the length of the function of coverage, and we can see that we obtain, there's no degradation in length when compared to the state of the art before us. That's the blue part here. So just to kind of wrap things up, I kind of sped through two different applications, site reaching and site inspecting. And we talked about an asymptotically optimal path following algorithm. Then I mentioned that we also care about placing the base of the robot and how do we optimize for that. Then I mentioned a new cost function that we care about for steerable needles. And I mentioned a resolution complete efficient planner for these systems. And this is kind of what we're most excited about recently. For site inspection, I mentioned an asymptotically optimal efficient inspection planning algorithm, where I think the key algorithmic contribution there is this notion of epsilon p dominance. And actually that sparked some work in the more classical planning communities. And we've since presented several works on bi-objective optimization that emerged from this line of work. So that was kind of cool to see that it moved to a totally different domain. This is all the references that I mentioned throughout this talk. And more importantly, I want to thank all of my collaborators. So on the top row, it's the PIs that I've been working with. This is Ron Alterovich, who is my main medical collaborator. Alan Kuntz was his student and now is a professor at the University of Utah. And Sid Srinivasa is my postdoc advisor, who was at CMU and now is at UW and Amazon Robotics. And we're all taking credit for the real work done by students. Mingyu Fu and Sherman Liaz are the main contributors. Mike did the work on modeling the forces of the needle. And obviously we have clinicians that helped us verify the relevance of our work. And with that, I'd be happy to take any questions.
Thank you, Oren, for the great talk. Let's open the stage for questions. You can simply unmute yourself and ask.
Thank you, Oren. We'll get started. It was a very, 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 very interesting talk, and a slightly different topic than what we're used to, but it's great. Now, the question is, first, a clarification. The inspection problem, is that a version of some kind of like a non-metric traveling salesman problem?
So in the traveling, it's very connected to the traveling. I want to put the definition. In the traveling salesman problem, and actually this is not a new problem. You can see some of Lydia's work way back where in some sense we have two computationally hard problems that we need to solve. We need to choose a set of points that we care about from which we can collectively see the entire set of points of interest. And this is what's called the coverage set problem. And then given these set of points, we want to compute some notion of a traveling salesman problem. So how do we traverse these set of points while returning to some constraint? So the TSP problem is kind of hidden in the background, just like you observed. And initial approaches simply said, okay, let's sample a bunch of points until we collectively see the entire set of points of interest. And then let's run some variant on TSP with neighborhoods, TSP, some that collects these points. This is the orienteering problem. So there's different versions of what you exactly want to optimize. Obviously, decoupling two computationally hard problems, there's no good reason for you to be able to produce optimal solutions. So these original versions do not claim any quality on the cost of the solution obtained. And admittedly, they were done before we had the machinery of RT star to produce optimal paths for a robotic system.
Okay, yeah, thank you very much. By the way, I also noted that I do like RRG much better than RT star actually. So I found it is that much more useful because essentially it approximates any optimal trajectory, even though you don't know the cost function a priori, right? So that's great. But so another thing is how, if you have to move to a medium like the human body, which is not necessarily homogeneous, I imagine that with a needle or something like that, you have some problems going through interfaces, right? So if you had to puncture a membrane or something like that, right? So I imagine that there are some issues with that. Is that something that you encounter, something that you have to handle somehow?
So I think we're just starting to scratch the surface of these problems as we try to make this more and more applicable. So I think there's challenges that we don't know how to address before we can look at that. So handling uncertainty, and when I say handling, I mean handling while giving rigorous guarantees, is really the biggest challenge I think that we're facing. Right now, we're looking, for example, for steerable needles, what is the right point to puncture? This is why it's very much related to your question. Where do we want to enter the body to be as robust as possible to uncertainty? And that's even before looking at the fact that the human body is not homogeneous, and how do we give a good model of the system. And these systems are really hard to model. It's not like a manipulator where we know everything about them, and everything we do there is also computationally expensive. So when I mentioned FK and IK with the manipulator, it's just a bunch of matrix multiplication. Here we need to run numerical simulations. So from an algorithmic perspective, this is really cool because it gives us a lot of challenges that we really want to re-examine. What is the computational bottleneck that we really wish to optimize over? For example, it's not necessarily collision detection. It's just looking at what the shape of the robot is. That is really complex.
Thank you.
Right. Any other question? I actually have one. It's more out of curiosity. So in the first part of the talk, you were showing some plots about errors. I think I marked it down. It was slide 22. My curiosity was, here you are comparing different algorithms. I wanted to see a bit, to know a bit how does real surgeon at the moment rank on these plots. So how far are you from reality?
Okay, so I think this. Wait, there's. I think we're talking. No.
It was 22, I think.
22. Okay. Yeah.
Oh no.
So,
maybe then I.
Yeah, no. This is the Forshape error. So.
Yeah, exactly.
So admittedly, there's still some work to be done. And here we're looking at the Forshape error, which is not that intuitive. When I mentioned on the steerable needles being clinically relevant, there we talk about acceptable errors of how far away we can be from a site that we want to reach. And I was sure that I'm going to get a lot of pushback, especially from guys like you, when I say that I can be resolution complete and say that I find a solution after a finite time. The problem is p-space hard. We cannot give guarantees. What we can say is that we don't have the motors of the system don't work. The surgeon doesn't care anymore how far away am I from the distance. So there is this minimal resolution that underneath that everything is noise. And if we're above that, then if a plan adheres to this minimal resolution, then we can find a solution. So we can actually have these values, and these are on the orders of millimeters. And we need to look at the specific error for the specific system. Right now, Rana Turovic with his group and with collaborators at Vanderbilt are looking at experiments in pigs, in pig lungs. And I think they're going to have a paper out pretty soon exactly talking about errors for these. What are these systems even capable of doing?
Thank you. Thank you. Very interesting. Any further question? Does it seem so? Today seems like a quiet audience, but I guess the audience can feel free to reach out to you in case they have interests or discussions. I think you had your email maybe in the first slide or in the somewhere you had maybe your email.
Yeah, I'm not sure if I added it here.
Oh, nope.
No, but
Then,
I'll write it in
I think
the chat.
we give, yeah.
Oh, Salzman. Yes. So really feel free to reach out, both from an application point of view. What excites me is kind of look at different applications and look at the computational challenges that arise from planning problems. So I'm working on this domain, and on the other hand, I'm looking a lot at, say, planning problems that arise for Amazon-like warehouses, and we're having discussions with Amazon people on a lot of their planning problems and optimization problems. So kind of crystallizing what are the computational challenges from different applications, giving rigorous guarantees is really what at my lab we're trying to do. And feel free to reach out and talk to me about that.
Great. Thank you again, Oren, for a very great talk, and good luck for the next steps. And thank you all for participating, and see you all next week for the next Autonomy Talk. Bye.
Thank you.